Next example. Of conditional expectations. Again from the blackboard example. But wasn't done in detail in the blackboard, so we will do it more detailed here. So here x and y are two continuous random variables jointly continuous random variables okay, such that, right, as was done in the blackboard, that if y, let me create another page so that it will, I can seamlessly go on there. Okay, so y given x equal to x naught, we gave this example earlier. So give y given x equal to x naught, we said was uniform in 0 x naught. This was done in the blackboard, right? So y given x equal to x naught, right, was a uniform distribution in 0 to x naught. Okay, for all values of x naught in omega x, and so x naught had to be a positive or at least a non-negative number. So let me write, I think in the board I wrote x naught greater than 0, so I will stick to that here. So x naught has to be basically a positive integer, but in a degenerate case can also be 0, but we will not worry about that, right? But basically x naught is taken from some prior distribution on capital X, right? And so what this means is that basically what it means is that the density function of conditional PDF of y given x equal to x naught, which is basically this conditional PDF, is basically 1 by x naught for small y, the argument of this conditional PDF between small 0 and x naught, right, and it is 0 otherwise. That's what is the meaning of this statement up there, that the distribution of y given x equal to x naught is 0 to x naught. Now, so this is the first point. So the second point is now, right, we also to proceed to find to write out the joint statistics, we also need the PMF of, or sorry, the PDF of x. So now let us assume that x given x by itself has the unconditional PDF, right, uniform 0, 1. Okay, so this is important, right? We need to be, I'll just put a box around this. Okay, x is a uniform PDF between 0 and 1, right? And y given x equal to x naught is uniform 0 to x naught for all any value taken by capital X. So that is what, right, this example is assuming. Okay, so basically now, so the goal is to find, the question is to find, right, the conditional PDF of, the conditional expectation of x given y equal to x naught. So that is a problem. Find the conditional PDF of x given y equal to y naught. We note that from this specification, that the conditional expectation of y given x equal to x naught, this was again done in the blackboard, is always going to be x naught divided by 2, irrespective of the distribution of x itself, right? So this you don't need to do any calculations. I think you just write the result out by inspection, that if you're given the PDF of y, conditional PDF of y given values of x, the conditional the mean can be straight away written out, right, and doesn't require any other information. Okay, but now we're asked to find the conditional expectation of x given y equal to y naught. So for this we need to do the whole analysis. So this requires us to find, right, requires a finding of all kinds of things, right, basically fxy and then fy. So from fxy and the joint PDF and the conditional and the marginal PDF of y, you can get the PDF of x given y also. So we need all these, we need to find this and we need to find this, right? We need to find fxy, we need to find fy, and then from that we will find the conditional PDF of x given y equal to y naught. Okay. So now let us start with fxy. What is the joint PDF of x and y? So we note that fxy of x comma y, or let me be more clear about it. Supposing fxy of x naught comma y is going to be equal to f y given x of small y given x naught multiplied by, so I will write here note or recall. So we know this, right? And this is true for all values of small I. So this is going to be true now for all x naught comma y in the set omega xy. This is a general result, right? No, in all cases. And in this particular example, let us first identify, of course, also identify the omega xy. Okay, so to identify omega xy in this example, so here, so we have x and y. Identify omega xy here. So as omega x is basically this interval 0 to 1, right? And given any value of x, right, the x-axis here, so this is omega x, and given any x naught, what we're saying is that for any x naught in omega x, y given x equal to x naught, I said was uniform 0 to x naught. So how do I translate that to this figure? That means that given any x naught here, let us say that value of x naught, that means that y takes values in 0 to x naught. So y, it takes values along this vertical line between 0 and x naught. So clearly, as a small x naught varies between 0 and 1 depending on the value taken by capital X, right, you get this particular triangular region as the set of values that x and y can jointly take, right. So for any x naught, right, no matter where it lies on this interval 0 to 1, the value of y is between 0 and x naught. So which means that omega xy basically mathematically is written like this: a set of all points in the xy plane xy such that 0 is less than y less than x. So y can never be bigger than x, right? And both x and y have to be between 0 and 1. So this is basically the set of values taken by x and y, and this is also the support region of the joint PDF, right? And so now it's fairly easy to so this is of course true only in this example. Okay, now we have we calculate, this is our fx omega xy that we found. So now we can easily write out the expression for fxy, right? That is so therefore what can we say now? We will go back to this and write fxy x comma y is going to be, in this example here, for this particular example, this fy given x is basically, as we pointed out, is already, right, known to be 1 by x, right, and that is the 1 by x naught here. So this is a f of y given x, right, and then 1, which is fx. So basically 1 by x naught. sorry, I should not, okay, let me put a x naught comma y, right? So fxy f x naught comma y is 1 by x naught. So basically fxy of x comma y is basically 1 by x for xy in that triangular region. Okay, and this equation is obviously true because there were this fy given x was 1 by x naught for any value taken by capital X, and therefore we can drop that subscript 0, and this is our joint PDF. So this is the, as we know, this is the joint PDF of x and y. So having done this, now we will next identify the marginal PDF. What is the marginal PDF of x of y in this case? That's what we need, right? The marginal PDF of y is basically now going to be got by, right, fy of small y. Now what are the range of values that y can take, right? So obviously y also can take the I will write it here. Y also will take values in 0. So clearly y has to the values taken by, as we already know, right, this is our omega xy, that triangular portion, and from this, right, omega xy, we can clearly see that y is also limited to the range 0 to 1, just like x, and therefore this fy of y is now going to be equal to, fy of y is going to be equal to, let me get it to stay here, is basically this integral. Now I'm freezing the right, I'm going to take this, let me, I think I should draw this again. So I'm going to now take, right, I'm going to assume that I'm going to freeze the value of y at some take some in the interval 0 1, right, and so if I freeze the value of y, then that means x can, right, the new omega x will be sorry, this should be y to 1. So therefore this will be an integral y to 1 of fxy x comma y, and obviously dx, right. It's an interesting PDF. So it turns out that this is equal to integral y to 1 by x dx, and this is basically, right, minus ln y, 0 less than y less than 1, less than equal to y less than 1. This is the PDF, marginal PDF of y. So it turns out that this is minus ln y, right, and it is not a uniform PDF anymore. Obviously it is a highly non-uniform PDF, right, and small values of y are much more likely than large values of y. This is a very interesting PDF, right. It turns out that minus ln y is an interesting PDF, which I think we are seeing for the first time in this course, and we know that it looks right, it looks like this, right, in 0 the range is 0 to 1. At 0 it takes unbounded values according to the ln function, but the ln function increases rather slowly, very slowly in fact, as you go towards 0, and so therefore it has unit area. So this is the curve minus ln y, and the area is unity. It has to be a valid PDF, right, and I urge you to check out the fact that it has a unit area by just simple integration. So minus ln y by itself, right, has the first time we are seeing it, it's also a valid PDF, right, okay, which you might not have seen up to now. Okay, let us continue. So this means that now, to continue with our example, which it means basically, let me pull out another page. So we have this, sorry, for x given y of x given y naught. Now this is going to be fxy of x comma y naught divided by this conditional PDF of x given y is basically fy of fxy of x comma y naught x comma y naught divided by fy of y naught, and this is basically this numerator term is basically this 1 by x, right, and divided by minus ln y naught, right? It's always better to just leave it as minus ln y. I'm not write it in a different way. I'm just sticking to that. So what is this x now? So x is now going to be this small x is in the so-called new omega x. What is this new omega x given y equal to y naught? And this new omega x is basically the set y naught to 1. Okay, that should be obvious from this picture out here. So let me actually write, whether you write as y or y naught, this picture applies here. And so the range of values that small x can take, capital X can take, the random variable x takes when you given the event y equal to y naught is the set of the interval y naught to 1, and that is what we have here. So this is the very interesting conditional PDF that we want, right? It's basically this 1 by x normalized by minus ln y naught, and obviously the small x, right? It only takes values from y naught to 1, and then what happens if the conditional expected value? So the conditional expected value that we want, x given y equal to y naught now. So it's basically going to be this integral from y naught to 1 in here, right? In this particular example, it is the integral is from y naught to 1 of x multiplied by this f x given y of x given small x given y naught dx, and that is equal to integral y naught to 1 of x into this thing from the top. Let me just simply, so this thing will come here. What does it become? It becomes 1 by x divided by minus ln y naught dx, and this is basically, as we said in the blackboard lecture, the x cancels, and this is 1 minus y naught divided by minus ln y naught. This was derived in the blackboard lecture, and let me write it again clearly. 1 minus y naught divided by minus ln y naught, right? And this number was between 0 and 1, as was between y naught and 1, as was pointed out, right? This number cannot be smaller than y naught, and it cannot be bigger than 1, right? And that gives you a couple of other interesting inequalities. One of them is a restatement of the inequality of the ln function itself, and the other is another inequality which is kind of interesting, that is lower bounded by y naught. And so this basically is the answer to our question that we set out to find. This conditional expected value, and this is what it is. So in summary, let me just state what we've done. So we found, summary, we found E of x given y equal to y naught by finding what did we find? We first found fxy, then we found fy, the marginal PDF of y, and then when we finally found the fx given y, and then so this was directly sufficient for us, right? So in this particular case, we could find a closed form expression for the conditional PDF of x. So this was what, right? This was sufficient to find the conditional expected value of x given y equal to y naught. So that's basically the blackboard example explained clearly, and I think, and so I will stop the example at this point.